I have about 30 more seconds left. Give me a thumbs up if you are finished. Okay. Keep working, you're good. Okay, so number one, we have 25% of 200. So who can tell me what that value is? Hayden James.
50.
The answer is 50. Hayden, how did you get 50?
I moved the decimal over 2 places.
Okay.
And then I multiplied.
Okay, so you did 0.25 times 200. Okay, good. That is correct. Did anyone else solve it differently than that? Are you raising your hand? Hayden?
I just did 200 divided by 4. 25%.
Okay. So he knew that 25% is 1/4. So 1/4 of 200 would just be 200 divided by 4, which is also 50. Good. So that looks like, thank you. So he knew that 25% was 1/4 of 200. If it's a whole number, it's over 1, which becomes 200 over 4, which is 200 divided by 4, which is 50. Good. All right. Number two, 12% of 200. Jordan, what'd you get? 12% of 200, you got 24. All right, Jordan, how did you do that?
I did, decimal over 2 places.
Okay. So she just moved the decimal, just like Hayden did in the first one, and got 0.12 times 200, and that equaled 24. Did anyone else do it different?
I guess I kind of did it complicated. So I put 10% of 200, which is 20, and then 2% is a fifth of 10%. So 1/5 of 20 is 4. And add 20 and 4.
Okay, so I get what you're saying. I'm trying to think how to write it. So you said 10% of 200, and then you said plus 2% of 200, and then you added them together. Okay, so 10% of 200 was 20, and then 2% of 200 was 4. So we added those together and got 24. Good. All right, I'll show you the way I did it because I did that way. I think if I would have had a calculator, I would have done it this way. But for that one, that's how I did it. But for this one, I said I knew that 12% of 100 was 12. And so since it's not out of 100, it's 200. So I just multiplied 12 by 2. Does that make sense? So I said, I come over here and write it. I said 12% of 100. Well, percentages are already out of 100. So 12% of 100 would just be 12. Okay, so I just did that twice. That gives me 24. All right, next one, we have 8% of 200. So who can do that just based off the way we just said? How could we do that one? What would it be, Hayden? It'd be 16. I don't know why I changed colors, but yeah. 16. 8% of 100 would be 8, but it's 200, so we double it. All right, and then finally, we have p% of 200. So how would we show that mathematically? How did we do it? Hayden, what do you think?
I just put X.
Do what?
I said I just put X.
Well, it's wanting you to come up with like how we showed the steps over here of what we did. It wants us to use the variable P instead of whatever percentage that we use. So what could we do? How could we show that mathematically? Well, we just did it 3 different ways. What did we do with our percentage each time? Okay, we move the decimal over. Do what? We multiply it by 200. Okay. Well, look at our percentage here. It's 25. What's our answer? So what did we do to it?
Double.
It doubled. For right here, it's 12. Then here it's
24.
here it's 8. Here it's okay. So what did we do to our percentage each time? Doubled it. So how can we show that mathematically? How do we show that we double something? We multiplied it by 2. So we could just put 2P.
I had to, I didn't put a B.
Okay, that's one way we did it. Okay. Or we took the percentage out of 100%. That's what we're doing when we move the decimal 2 places. They're saying the percentage divided by 100. That's us moving the decimal. That's what this represents. And then what did we do when we move the decimal? You times it by 200. Okay, so either one of those options would have worked. All right, moving right along. 1 second.
Just for the, in 6th grade, did you tell like teachers like the butterfly way, like you do this way and then you do it that way?
When you are simplifying fractions, you can do that.
So I didn't know if it was percentages or
That's when you have 2 percentages set, or when you have 2 fractions set equal to each other. So like, if I had, this is just a side note, this does not have to do with this lesson. If I had x over 100 equals 2/3, anytime you have a fraction set equal to a fraction, you cross multiply. So that would be 3x equals 200. And then you can solve for x, which is not a whole number. It's not an even number. I hate that that's the answer, but that's the answer. 666. We'll add a 7 there. Okay, so yeah, that has nothing to do with this lesson though. Next, but it does come into play when you are dealing with percentages, but that's only if the fractions are set equal. Okay, so next part, we have these 3 figures called Platonic solids. Okay, so I want you to look at these, and I want you to answer, in what 3 ways are these figures alike, and what 3 ways are these figures different? I don't want you to look at your book. I just want you to look up here at mine now. Okay, we're just going to talk about it. Okay, let's talk about first how all of these shapes or figures are alike. What do they all have in common, Tyler? They all have angles. Are you talking about these things right here? Okay, so those are, yes, they all have these little points. They're not actually called angles though. Who knows what those little points are called? Starts with a V. Courtney. Vertices. Good. Okay, so they all have vertices. I don't know if I spelled that right. No I here. Just an E. Cool. All right. What else? Jordan. They're all 3D. Correct. What else? What else do they have in common? They all have these vertice points.
But these and edges the same one.
Mm-mm. No, the vertices, these are the vertices. And then you said they all have these right here, edges.
Yeah.
Good. All right, so all of these shapes have edges. Okay, good. What else do y'all notice?
They have faces.
They all have faces. Good. Try to like point at one. Okay, so we've defined some good vocabulary. The points where all of them intersect is a vertices. Like the sides that are connecting the vertices are called edges, and then these different whole shapes here are called faces. Are all the faces the same for each shape?
No, like
Okay.
some shapes have more faces.
Okay, so let's start pointing out some differences. What are some differences that we notice? Jordan,
They're different shapes.
every face is a different shape. So every face is different shape. All right, what else? Tyler,
Different amounts of vertices.
different amounts of vertices. Good. Liz,
They have different amount of edges.
different amount of edges. Just going to add edges to the end of that sentence. Different amount of vertices, edges. What else?
The faces.
And faces. Good. Okay. So what is this one? We said every face is a different shape. What's the face of this one?
Like what it's called.
Yeah, what kind of shape is it?
Triangle.
Triangle. All right. How many does it have? 4. Okay. What about for the cube? It's got a square face. And how many faces? 6. All right. And then we got a dodecahedron. Okay. What kind of face? 5 sides. Pentagon. And it's a dodecahedron. So how many faces?
Isn't that 8?
Kind of 12.
Oh, dodeca. My bad. Yeah, 12. Sorry, emphasize the wrong part of the word. Good. 12 faces. Now, these are all, once again, they're called platonic solids. That's not like a huge thing you have to know for this unit. That's just what they're called. So we got a tetrahedron, which is just this guy, the little pyramid looking thing. We got a cube, and then we got a dodecahedron. So looking down at your paper again, you can look in your books. It says the table shows the numbers of vertices, edges, and faces for the tetrahedron and the dodecahedron. Okay. Let me read this. Number 1 is on the next page, but it says complete the missing values for the cube. Then make at least 2 observations about the number of faces, edges, and vertices in a platonic solid. Okay, so I'm going to give y'all about 2 minutes. I want y'all to go in and fill in these spots here in the table. So you're going to have to go up here to the cube and count all the vertices, count all the edges, and then I want you to look at the table and make some observations. So I'll give y'all about 3 minutes to do all that. Ready, go. I'm going to walk around and help you if I need to. You want me to check it when you're finished? Just raise your hand. I'll come by and check. make your observations on the next page on number 1. Just try to come up with at least 1, 2 if you can. About what you notice in your table. Okay. Next little page over here. Let's see if I have those. All right, make sure you're making some observations about what you notice in the table. Okay, compare the faces and the vertices and the edges for each one. What do you notice? Okay, let's look at it. So for the first one, for the faces of the cube. So here, if you are more of like a, you need to see. Yeah. So when I'm looking at this, the faces are all of the flat surfaces on here. So I have the top and the bottom, I have the front and the back, and I have the side and the side. So how many faces is that? 6. Okay. All right. So then I'm looking at all the vertices, which are all these little corner pieces. So I have 1, 2, 3, 4, 5, 6, 7, 8. So how many vertices? 8. And finally, my edges. So I have 1, 2, 3, 4 on the top, 5, 6, 7, 8 on the sides, 9, 10, 11, 12 on the bottom. So how many? 12 edges.
I needed that key.
Sorry, I should. I meant.
Messed my eyes up and I was like,
I always forget to get these out for my first class. I also found a tetrahedron, yeah. But they already gave those to you, and I don't have a dodecahedron. Okay, so looking at this chart, I know it gives you space in number 1, but just so I can keep the chart up here, let's make some observations, okay? What do we notice about this table here? Hey, what do you notice?
They all have even numbers.
Okay, they're all even numbers. Where's my orange pen? All these colors are too dark. I think I have it on the desk like that. Can y'all see that color? All values are even. Good. All right, what else do you notice?
The more faces you have, the more vertices you have.
The more faces you have, the more vertices and edges you have as well, okay? The more faces you have, I'm gonna shorten it to V and E. Okay, so that stands for vertices and edges. So hopefully that doesn't confuse anyone. Okay, so would you agree with me if I said there's a relationship between the number of faces to the vertices and the edges? Okay, that's what Hayden just said by making this statement right here. And I agree with that. Okay, So what we're beginning to understand is when we see those relationships where it happens every single time, you can create an equation from that. That's what we're kind of building to. Okay, Tyler, what do you notice? There's always going to be more vertices than there are edges.
No, more vertices and edges than there are faces.
Oh, okay. Got it. There are always more vertices and edges than there are faces. I'll label those real quick just so y'all know what I'm talking about when I use these letters. Okay, good. All right, so let's kind of like hone in on just like the cube for a second. We're just going to hone in on this cube. So we already discovered there's a relationship between the number of faces and edges and vertices, like they're all like interconnected. Okay, so how could we get to that? What do y'all think? What do y'all notice as we just hone in on the cube? Even, I mean, you can even look at it here. So tetrahedron, it's 4, 4, then 6. 6, 8, then 12. Okay, we'll come back to this, okay? Because if we're not seeing it yet, we're gonna go forward and then we're gonna come back, okay? All right, so let's look at number 2 on the next page. So we just did all those observations on number 1 around the box. So we did that. So number 2, so we just said there are some interesting relationships between the number of faces, edges, and vertices in platonic solids. For example, the number of edges is always greater than the number of faces. That's kind of what Tyler said, okay? So I want you to underline that. The number of edges is always greater than the number of faces, okay? So they gave us E is greater than F. What did they just give us? What's that vocabulary word we just learned yesterday? Constraint. So with a platonic solid, a constraint is that your edges are always going to be greater than your faces. If you have an edge or a face that's greater than an edge, you've done something wrong. Okay, so it says another example, the number of edges is always less than the sum of the faces and the vertices. Okay, so look, that's also what Tyler said. Let me make sure I get that. The edges is less than when we add up the faces and the vertices. So if we say 4 plus 4, that's what? 8. Is 6 less than 8? Yep. 6 and 8 is what? 14. Is 12 less than 14? Okay. 12 plus 20 is 32. Is 30 less than 32? Did you notice the similarity of how much they were off of the vertices each time? How much were they off by? Interesting how that happened 3 times in a row. Okay. So there is also a relationship that can be expressed with an equation. So circle equation. Okay, because that's what an equation does. It expresses a relationship between values. Can you find it? If so, write an equation to represent it. Okay, so there is a way you can always take the edges, the faces, and the vertices and put them together mathematically to find one of the other ones. Okay, so go back here. See if you can figure it out. Okay, we kind of just almost did it earlier. So I'll let you try to do that on your own. If not, don't panic. We are going to talk about it together. If you are so confused, I just want you to try to think of it. That way, when we talk about it, you say, oh, yeah, that makes sense. Okay? Try to see if you can figure it out. And you may just think of it a different way than someone else. That's fine. Basically, it's saying we can take the faces and we can take the vertices and do something, and it would equal the edges. We can take the faces and the vertices and then do something else, and we'll have our edges. You don't get it, just think. Have that struggle. It's okay. It's good to struggle a little bit. Don't give up. It's only for a minute. It's only for a little bit longer. You can keep going. 30 more seconds. Try to figure it out.
I think I got it.
Is that what it is?
Over here, I mean, I got this one, I got really six, and I got four, and I got two.
Okay, so that is a part of the relationship, or that is something that happens every time. I don't know. If that's how. You're good. It's okay, I promise.
Yeah, it is there too, so.
All right, so Hayden James found even in a different way how there is still a relationship there. How do I word it? They are they're increasing at the same rate. So the ratio of the numbers here is the same as it gets bigger, okay? But there's something that we do to all of these variables that will work every single time we're trying to find the faces or the edges or the vertices. So Hayden Brinkley, what did you get?
F plus B minus 2.
Okay, write that down. We're not going to panic yet. We're not intimidated by this. We are learning how to do it still. Okay, so Hayden saw the relationship in the table and said, okay, let me go here. Let me fill it in for us. We said, what was it, 6, 8, 12? Okay, so Hayden said, if I take the faces and the vertices and I add them together, what do we get? 8. Okay, and we said that just like the constraint said, the edges is always going to be less than the faces. Was 6 less than 8? How much less than 8 is it? 2. So he took the faces and the vertices, added them together, and then he subtracted 2, and that equaled the edges, right? Okay, let's see if it's true for the next one. What's 6 plus 8? 14. If we said 14 minus 2, what would we get? Is that true? Okay, what about this one? 12 plus 20, what do we get? 32. What's 32 minus 2? 30. So do you see how that relationship would work for every platonic solid? Yes. Okay. If you did not get this, it's okay. Creating equations is not just the super easiest thing, okay? But do we understand how this expresses that relationship from the table?
Yes. Okay,
good. That's really what you should be able to take away from this activity. Good. Okay, so that's one way you can express it. You can have it solved for E. So this equation is going to help us find what? The number of edges. Okay, that's what this equation is going to tell us. Okay, now there's always ways you can rearrange an equation to help you solve for whatever you're looking for. Okay, maybe we had that chart filled in and the faces part was left blank and it told us how many edges, okay? Then you can rearrange your equation and solve it for different parts of it. Okay, let's look at this last little bit. Blueberries and earnings. I really like this activity. I think it's a very good little kind of sum up, a little bit easier than the platonic solids because it's more what you are familiar with. So it wants you to write an equation to represent each situation. I'm going to do the first one with you, and then I'm going to let y'all try to attempt the other ones on your own. Okay, then we'll come back together and we'll talk about it. Okay, so it says write an equation to represent each situation. So the first one, it says blueberries are $4.99 a pound. Okay, that's important to know. So blueberries, $4.99. Okay, and Diego buys B pounds. So if I'm looking at the variable B, what is it talking about? Pounds of blueberries. Yes, sorry. And he pays $14.95. Okay. So blueberries are $4.99 per pound. Diego buys B pounds of blueberries and pays $14.95. So because they chose to represent pounds of blueberries as a variable, that means that that value can change depending on how many pounds you buy. Okay. So how could we represent each pound is $4.99 and we're going to spend $14.95. How could we represent that in an equation? Okay, I want you to think of it this way. Let me get a piece of paper. Okay, so we just said blueberries are, what was it, $4.99? Okay, $4.99. All right, how many pounds of blueberries do we want to buy? We're going to the store. This is not related to the paper, but we're all going to go buy some blueberries. How many pounds do we want to get? 5. Okay, I'm going to buy 5 pounds. So how am I going to figure out how much I'm going to spend? Hayden? So I'm going to take $4.99 and I'm going to multiply it by 5. All right, so we're going to spend $24.95 on blueberries. Now, what was the value, according to our paper, that said that can vary depending on the B, which is what? Pounds. So this value can change. So instead of putting a 5, what are we going to put? B. So we're going to put $4.99 times B, or just $4.99 B. Okay, so we have $4.99 B, but this time it doesn't tell us how much we're buying, it tells us how much we're going to spend. So how do I show the $14.95?
You would say
All it wants us to do is to write an equation. It does not want us to solve it. You could.
well, it's not an E, it's heavy decimal. Because if you do 499 times 3, it's 1497.
Yeah, it's like a big long decimal. All right, so that is your equation. That's all it wants you to do is just to write an equation for each situation. Okay, so when you're thinking about what the equation would look like, come up with values for those variables and see how you would actually solve it in a real world situation, and then just represent it mathematically. Okay, please just do your best. Okay, we will talk about it together. Do not stress or worry yourself to death. Ready, I'm going to give you about 5 minutes. Ready, go. Thank you, sweetie.
You and I one B, right?
Yes, ma'am.
So, brother?
Say it again. Noah's, mine is 45 more than Noah's, and Noah's would be the most that equals mine. Okay, or you could take mine and subtract. Okay. This much and it would equal Noah's.
Yeah, I was in a mistake, I couldn't see it.
Yeah, it's kind of worded weird on that one. And that's what, but they do try to do that to you, so you have to think about which order it goes in. Yes. All right, y'all have about 2 minutes left. If you want to like move next to someone and talk through it with them, please keep your mask on and pulled all the way up over your nose. Y'all can compare your answers. Ivan, would you like me to check yours? If you want me to check your answers like you need to. But now we like to do it again.
Like, I put it down, but I don't know how long this will.
Okay, so we're not long. So, okay, let's borrow our own schools. Okay, so. Okay, so we earned $75. So we earned $45 more than he, so we made more money. So, and Abigail, you said, I make $45 more. How would they find out how much they made? They would take how much you made and do what? Divide. That's what we made, 45 more. So we just subtract off 45, right? Okay, so we just say, how much you made, $45 minus $45, or your amount of hours. Just like how much. Right, yeah. Yes, ma'am. Okay. Same situation. But now, Noah earned $3 over the cost. I earned $10, which is 45, and then I did, based on the setting, 275, I mean, Now I earned $11 over the summer. Okay, so now it's $70 what it is. I earned X dollars, so now X what it is, which is $Y more than that. So this is X minus Y equals, okay, let's look at it. Remember, we are not stressing. This is lesson 2 of a very long unit. We will get it. Okay, same situation. We're still talking about blueberries. They're $4.99 a pound. Jada buys P pounds and pays C dollars. How would we represent that as an equation? Hayden James.
4.99.
Okay. Good. All right. And C, what about that one? Jordan.
We divide Q
Times Q equals C. Good. All right. So you can see from A to C, it's the same situation, but what did we slowly do? We got rid of the numbers, okay? Because in any situation that you go, any individual store, all blueberries are not going to cost $4.99, are they? Nope. We're not all going to get the same amount of blueberries, are we? Therefore, what's going to always change? The total cost, okay? So that's why we represent them with variables instead. Okay, new situation. Now we have Noah earned in dollars over the summer. May earned $275, which is 45 more than Noah did. Okay, Abigail, what did we do to get this one? 275 minus 45 equals N. Is that the only way we could do that one? That is correct. So if you did this, you are correct, okay? What is another way we could have done this? Tyler? 275 minus N equals 45. That is also correct. Did anyone else get another way they could have done it? Hayden?
45 plus N equals 275.
That is another way you could have done it. Okay, so what I want you to understand in this situation is that for this example, these are called, write this down, equivalent equations. Equivalent equations. The word equivalent means that it has the same value, but it looks different. Okay? The same way 1/2 is the same thing as 2/4, right? Those both represent 1/2, they just look different. Do y'all agree with that? Because those are equivalent fractions. These are equivalent equations because the same situation can be represented differently. For example, this one, you have it solved for how much Noah made, whereas these, we would have to rearrange our equation and then end up having to solve for Noah. Okay, now I'm just gonna stick with the first one y'all say for the next two, so we don't have to write all three. But what about for part E? What did we get? Abigail? M minus 45 equals V. Finally, for F, what did we get, Liz?
X minus y equals W.
Good. No, why did I put 12? Where did the 12 even come from? That's concerning. Okay, number 2. How are the equations you wrote for blueberry purchases like the equations you wrote for May and Noah's summer earnings? How are they different? Okay, so let's talk about how they are alike. How are they all alike, Jordan?
They started off as numbers and then they moved to variables.
Good. Started as numbers and moved to variables. Good. All right. How are they different? Or can y'all see, I'm sorry, are there any more things y'all found that were alike about them? Do they all work with 3 quantities? Yeah, they did. You don't have to write that one, but they did. All right. What about how are they different? Hayden?
With the blueberries, you were multiplying to get the total, and with the earnings, you were subtracting the adding.
Okay, so blueberries, I'm just gonna write blue. We multiplied. All right, for the summer earnings. We subtracted. Yay. All right, so I think it's beginning to make, hopefully, you're finding those connections between those real world situations being just represented with an equation that just models that relationship that's happening between all those numbers, that you can go into any place and that equation still works for it. It's not specific to a, like, this one is very specific, right? This is talking about somewhere there's a place, we're going to Walmart, blueberries are $4.99 and we're spending $14.95. Here, this is gonna work for any grocery store we go to. Any price of any blueberries, however many pounds you wanna buy, that's gonna represent the cost. Okay, so it gets gradually more specific. All right, car prices, we're not doing that one. On to the lessons, wait, just kidding, I may have to do a lessons synthesis. Okay, I did all that. Wait. I think I lost a page. I don't know what the heck happened. I've lost a page. Where's the lesson summary? Oh, here it is. I have the page. Okay, here we go. I have the page backwards. So, okay, so this kind of goes with what I just talked about. So we can use numbers and letters to represent the quantities in a situation. Oh my gosh. When might it make sense to use only numbers? Okay, so for example, like these, we mainly use numbers. When is appropriate to use only numbers, Tyler?
When you, like, know the classes or when you know exactly what the numbers should be.
Okay, when you know exactly what the number should be, that is an appropriate time to use the numbers. When is it more appropriate to only use the letters? Hayden James.
When you don't have the prices and the numbers, you just have.
Good. You've heard the phrase a quantity that varies and a quantity that stays constant. In this lesson, describe what they mean in your own words. If possible, give an example of a situation that has a quantity that varies and a quantity that stays the same.
Are you reading the car prices?
No, these questions are just on my little paper to ask, just to remember to ask y'all. So what are examples of quantities that change? So think back to the pizza party, or think back to, the blueberries and stuff. What were quantities that could change? And if you can tell me, what did we do in that situation, Hayden?
Like the number of students.
Okay, so when we were planning the pizza party, the number of students could change. So what do we do in a situation where that value can change? What do we change it to? A variable. Good. Okay. So what about situations have we talked about where the variable is, or the value is, the quantity is constant? Doesn't change. Y'all think of a situation like that? Hayden?
What budget or something?
Okay, yeah. If you had a constraint that you were working with, it had to be like, and it had to be to that amount or less. Yeah, good. All right, so let's go to the lesson summary now. Can someone tell me what page that's on? 142. All right. So we have a situation here. It says, suppose your class is planning a trip to a museum. Highlight. The cost of admissions is $7 per person, and the cost of renting a bus for the day is $180. What did they just give us there? The exact numbers, okay? Those are our constraints, okay? So when they give us those values that we're having to work with, those are our constraints, okay? So that's the kind of stuff we have to work with. So, gotta fix this paper, it's printed backwards. It says if 24 students and 3 teachers are going, we know that the cost will be done this way, or we could have solved it this way. If 30 students and 4 teachers are going, we could have done it that way. All right, first 2 paragraphs, put them in a little bracket. Okay, we're gonna put a little 1 beside this. All right, so it says, notice that the number of students and teachers can vary. This means that the cost of admissions and the total cost of the trip can also vary because they depend on how many people are going. Highlight. Letters are helpful for representing quantities that vary. Okay, so we're gonna underline letters, quantities that vary. If S represents the number of students who are going and T represents the number of teachers and C the cost, we can model the quantities and constraints by writing this. Teachers and students, however much we have, we're gonna add it together, multiply it by 7, and then add 180 because that is how much we have to pay for the bus. Okay, what values are not going to change in this situation?
The 180.
The 180 and the 7, which were our what? Our constraints. Okay, those are the values that don't change. Those are our constants. Okay, Next two paragraphs, or next three paragraphs, I'm sorry. Put a little bracket. Okay, I'm putting a 2 beside this because this is a second way you can look at it. Some quantities may be fixed. Okay? Underline fixed. What do y'all think that means? They don't change, so write that. Fixed means don't change. In this example, the bus rental costs $180 regardless of how many students and teachers are going, assuming only one bus is needed. Letters can also be used to represent quantities that are constant. We might do this when we don't know what the value is or when we want to understand the relationship between quantities rather than the specific values. For instance, if the bus rental is B, we can express the total cost of the trip as this. No matter how many teachers or students are going on the trip, B dollars needs to be added to the cost of admissions. So there's that new formula. Because depending on the bus rental place, that could also change. Or if you needed more than one bus, that could change. All right, that is your lesson summary. Your homework has already been posted, and you have 30 minutes left to look at it. Sunday.